Now we set up a microwave signal and transmit it through the given setup and observe the output through slaughter waveguide. Now we'll measure the VSWR or reflection coefficient of our antenna first. Okay, it's simple. We measured signal from our slaughter waveguide. Okay, and if the reflected signal is there, means if there is a mismatch between waveguide or the transmission and the load impedance, characteristic impedance of our waveguide and load impedance, there will be a reflected wave inside the waveguide. Okay, we can measure the reflected wave with the help of this slaughter waveguide, because in this slaughter waveguide we cut a slot such a way that we can observe signal strength at different point without affecting the field distribution inside this waveguide. Okay, we'll show you. Now we observe some output, and if we move this slaughter waveguide, the signal strength will vary because of standing wave inside the waveguide. It's not a sine wave. You can observe that it's a square wave whose amplitude is varying with respect to the position of position in the waveguide. Okay, because the reflected wave signal phase vary with respect to distance from the load. So we can observe like this. Okay, for VSWR measurement, we just need to measure the maximum and minimum value of this total signal or this standing wave. That's all for VSWR measurement. For antenna, first we'll move this on and we'll observe the variation. Okay, and it is moving. We'll put into some lower division value, 10 or something. Okay, and we'll move down. Okay, so here we can observe the variation in a zoomed manner. Okay, here it is decreasing. If I move left, it is increasing, and this is the maxima. Okay, this is the maxima value, maxima variation. I will move back. Will move upward. Okay, this will be the maxima strength of this signal. Okay, to get the exact maxima, I zoom to the top portion and vary it, and here it's shown that this will be the maxima 1, 2, 3, 4, 5 and 5.4 division. So for antenna, the Vmax equal to 5.4 division into we took peak to peak, and division is in 20 milliwatt, so it is 100, and for division on, okay, division means exactly it is 5.8 100 and 116 milliwatt, because here it is one entire division is 20 milliwatt, one small division is 4 milliwatt, because one big division consists of 5 small divisions. Okay, and we will move this on to find the minima value. Okay, it's moving, and here it is varying. To finding exact position, I am zooming to the instead of 25 milliwatt, and we'll move down. Okay, and then we'll move this one. It's increasing leftward, so we'll move rightward slowly. Here we'll get the minima value. Okay, it's again increasing, so this will be the minima value, and we'll go back to 20 itself. Okay, here we can measure 1, 2, 3, 3.3 division here, so 3.6. Here V minima is 3.6 division into 20 milliwatt, that means 60, 72 milliwatt. From this we can find the VSWR, which is equal to Vmax by V minima, at it is 116 divided by 72. Just calculate it. Okay, you can do the experiment in lab. And next we will use a termination other than antenna. Okay, here we'll connect this termination to the load and then record the Vmax and V minimum. Now we connected termination as load. Instead of our antenna, we connected another termination having another load impedance. And now we will measure VSWR of this termination. For that also we'll move through the slaughter waveguide. We can observe the variation here also. So the variation, okay. So we need to find the maxima and minima of this variation. So here we can observe a maxima. To get the exact maxima, we'll zoom it to the signal. Oh, it's 5 and okay, and we'll vary the norm, and it's decreasing. So we'll move back, and this will be the maxima point. Okay, we'll observe the maxima and we'll zoom out to 20 milliwatt and we'll get the exact value here. Okay. From here there is a 1 division, 2, 3, 4, 5. Oh, here also the maxima is almost same, 5.4 itself. So here also the Vmax is 5.4 division or 5.8 into 20 milliwatt, it is 116 milliwatt. And second, we need to find the minima of the load. For minima also we'll move. This will be the, here we'll get minima. For that also we'll zoom first. We can observe the variation in zoom down. Here it is decreasing, minima increasing. So when we move to minima position, this will be the minima value here, and we can observe that value as now the division is in 10 milliwatts, and it is 1, 2, 3, exactly 4 divisions. So we'll get 4 into 10 milliwatts, which implies it is 40 milliwatt. This will be the VSWR of this matched, normal termination or unknown loads. Vmax by V minima, which is 116 divided by 40. You can find that. From this VSWR or reflection coefficient, we can find the unknown impedance or the normalized impedance from a relation. I think we have an experiment to find unknown impedance also. That will do later. And this is the simplest experiment to measure VSWR of an antenna or any load. Okay, so just we need to measure the maxima and minima of our standing wave. That's all. Now we'll go to the second experiment, that is verification of relation between lambda g, lambda c and lambda 0. For that also we are using the same setup and same equipments. Here also we are using this termination to do the or to find the relationship or to evaluate the relationship between lambda 0, lambda g and lambda c. So in this case, first we need to find lambda 0. Lambda 0 means the frequency or wavelength of actual microwave signal. That we saw that we can find it using this frequency tuner. When we rotate this frequency tuner, and if the tuned frequency of this tuner is matched to the transmitted signal frequency, then the tuner will attenuate that signal, or it will absorb the power of that signal, and our signal strength will reduce. Okay, first we'll do that one. So here we can move the frequency tuner to change the tuning frequency of this tuner. Okay, and at a particular frequency of this tuner, we can observe a dip in the output signal, or a reduction of output signal power. That means the tuner is tuned to the actual signal frequency. If we measure the tuned frequency, we can identify our transmitted signal frequency. When tuned frequency is equal to the transmitted signal frequency, we will observe a dip in the output signal, or a reduction in the output signal. Okay, so transmitted signal frequency is fixed, we can't vary that one. Here we can vary the tuned frequency. Okay, and this tuner consists of a horizontal line section and a vertical line sections, and in between, or the in between these two horizontal lines and the cross section of this vertical line, there we will get the actual reading. That means here in this point, this tuner is tuned to frequency that is at a here 9.98 and 9.96 to 9.98, in between that, and the middle is 9.97. So this one indicating 9.97 2 gigahertz. Oh, sorry, my mistake. Sorry for this. Here it indicating